Thank you. I'd like to thank the organizers for the invitation to talk here. I've been really enjoying my stay so far. So I'd like to begin with a statement of Hilbert's fifth problem. So Hilbert's fifth problem is the following question. If G, a topological group, is locally Euclidean, in other words, it's a manifold, is G a Lie group? In other words, does G carry a smooth structure for which the group operations are smooth? In other words, so another statement is, suppose when we define the notion of a Lie group, we exclude the smoothness hypothesis. Just say it's a topological manifold with continuous group operations. Do we get any more exotic examples of groups, or is everything in this class just a Lie group? So this was, of course, 1900. It took about 50 years for the solution. The answer is yes. So you can put a smooth structure on any such group. And this is due to Gleason and Montgomery-Zippin. Around 1952. In fact, the smooth structure is unique, although existence is really the point. That's the difficult part. Uniqueness is sort of an exercise. Now, a lot of what Gleason and Montgomery-Zippin did was addressed in a much more general setting of locally compact groups. And only at the end is this locally Euclidean hypothesis used. And so, in fact, Gleason stated some conjectures which were subsequently proved by Yamabe. And a result is a classification of all locally compact groups in the following form. So this is called the Gleason-Yamabe theorem. Which is the following. So let G be locally compact. Then for all open subsets of G which contain the identity, open neighborhoods of the identity, there exists a subgroup G prime, which is open, and a compact normal subgroup K of G prime, which is contained in U, such that G prime modulo K is a Lie group. So what is this saying? Suppose for a second that we could always choose G prime equal to G. Then this is saying that in arbitrarily small neighborhoods of the identity, we can find compact normal subgroups such that the quotient is a Lie group. Now, taking such open neighborhoods converging to the identity, we see that G itself is an inverse limit of Lie groups. Now, of course, this isn't going to be true because, in general, G prime is not all of G. But we can choose G prime independent of U. In other words, there exists this open subgroup, and G prime is itself an inverse limit of Lie groups. So, I mean, this is a great theorem. It's saying, oh, we need this, given only this weak topological hypothesis on G, we can say a lot about, we can reduce the group structure of G to an inverse system of Lie groups, which is more understandable object. Right. So I'd like to isolate a particular case of this theorem, which is the following corollary. So G is a locally compact group. Then, if G is NSS, which I'll define, then G is a Lie group. So NSS is no small subgroups. It simply means that you can choose some neighborhood of the identity which doesn't contain any non-trivial subgroup. For instance, a Lie group has no small subgroups. You can see that by considering the exponential map parameterizing a neighborhood of the identity. In contrast, for example, any infinite profinite group does have many small subgroups, and as a consequence is not a Lie group. So I stated this as a corollary, but this is perhaps a little bit ahistorical because as far as I understand this, the proof of the Gleason-Yamabe theorem goes through first proving the corollary and then proving the theorem. Right. So let's put this all the way up there. Oh. Right, so this is the usual interpretation of what Hilbert meant when he wrote his fifth problem. There's another conjecture known as the Hilbert Smith Conjecture, which is a stronger conjecture which is still open. So that's the following. So let G be locally compact with a faithful action on a connected manifold. So in other words, I just mean we have an injection to the homeomorphism group of some manifold. Then G is a Lie group. So I'm giving homeomorphism group of a manifold the compact open topology, which is just the topology of uniform convergence on compact sets. Right. This conjecture is strictly stronger than Hilbert's fifth problem, because if you have any topological group, it acts on itself by left translation, and this is a faithful action. And if the group is locally Euclidean, you have a faithful action on the manifold, and so the Hilbert Smith conjecture tells you that G is a Lie group. And in the other direction, however, we can use the Gleason-Yamabe theorem, namely the solution to Hilbert's fifth problem, to reduce this to a rather more concrete statement. So an equivalent formulation of the Hilbert Smith conjecture is that there does not exist a faithful action of the p-adic integers on a connected manifold. So here I should define p-adic integers as the inverse limit of z mod p to the k z. So this reduction to this special case is essentially just an application of the Gleason-Yamabe theorem and a little bit more, namely Newman's theorem, which I'll mention later. Right, so one remark to make is that if we want to address such a conjecture, we may assume, without loss of generality, that this action has small orbits. This action of Zp on a manifold has small orbits. Why is this? Well, Zp has these subgroups, p to the k times Zp, and p to the k times Zp is itself isomorphic to Zp. So given any action, this subgroup, of course, also acts faithfully, and so we can just consider the action of that subgroup. And by picking an arbitrarily small subgroup, we get small orbits. Okay, why should we expect this to be a relevant remark? Well, according to the corollary, sort of morally, the property of Zp, which keeps it from being a Lie group, is the existence of small subgroups like this. So one should perhaps expect these small subgroups to play a role in excluding an action on a manifold. In other words, the philosophy should be something like the profinite topology is incompatible with the Euclidean topology of a manifold. Yeah. Z acting on Hilbert Smith? I mean, that's a Lie group, zero-dimensional Lie group. Z. Okay. Okay, so I said this is conjecture about sort of small orbits. We think, or at least if you believe the conjecture, you would believe that groups can't, or compact groups can't act on a manifold with small orbits everywhere. So I say, given the manifold, the question is what does it mean to act with small orbits? Say, a target statement which would imply this would, and is in fact equivalent to it, would be that for any manifold and any metric on that manifold, there's an epsilon such that an action by a compact group for which all the orbits have diameter less than epsilon must be the trivial action. So, in fact, there's that precise statement is true if I replace compact group with compact Lie group, and this is a theorem of Newman, which, although it doesn't itself necessarily have any bearing on the Hilbert Smith conjecture, it at least illustrates well the philosophy or one reason why we might expect groups acting on manifolds to have large orbits. So the statement is, let U inside Rn be an open set, and suppose, just to fix length scales, that it contains the ball of radius 1. And suppose the integers mod p acts on U with orbits of diameter, say, less than 1/10. In this case, then the action is trivial. All orbits, yeah. Yes. So the proof, or at least the idea of the proof, is very simple, so I want to say what it is. So let phi from U to U generate Z mod p, and we're going to define f from U to Rn by sending a point x to simply the average over the orbit averaging map. 1 over p to the I of x. So on the one hand, the orbits have small diameter, and so this function f is very close to the identity. F minus the identity is less than 1/10. And what this means is that the degree of f is equal to 1. Degree meaning the topological degree. I pick a generic point in U and take the, or in U and take the inverse image and count the inverse images. That's the degree. On the other hand, there's a factorization. If I look at f from U to Rn, f only depends on the image of x in the quotient by Z mod p, the space of orbits. So we have a commutative diagram like this, and this map here has degree p, at least away from the fixed locus of phi. So this tells us that the degree of f is divisible by p, away from the fixed locus of phi. So this is a contradiction unless phi fixes everything. Now, people have tried to generalize this this approach to address the Hilbert Smith conjecture. Zp, the p-adic integers, has a Haar measure, so you can construct this orbit averaging map just fine. With small orbits, the degree is 1. The problem is sort of in generalizing the second step. It's not really, this quotient is less nice of an object, and it's not so clear how to make the degree divisible by p. Right. So there's a restatement of Newman's theorem. In the following sort sort of perhaps more intrinsic language. So let G be a compact Lie group acting on the manifold M with metric D. Then if you have all orbits, if all orbits have diameter less than or equal to epsilon, which only depends on the manifold and the metric, and is positive, implies that the action is trivial. So why is this equivalent? Well, given the manifold, I can take a small open set and embed it in Rn. And then any compact Lie group has many finite subgroups, finite cyclic subgroups of prime order. And if such a cyclic, so if the whole action of G has small orbits, the action of the subgroup has small orbits, and then you conclude the action of every such subgroup is trivial. And so this theorem follows from the more concrete case considered there. Okay, and the reason I wanted to state it like this is because is just to illustrate the connection with Hilbert Smith Conjecture. Namely, if you take out this word Lie, then this is equivalent to the Hilbert Smith Conjecture because you apply it to ZP, and you conclude that after passing to these small subgroups, that the action is trivial. So there's a number of partial results towards this Hilbert Smith, which I should mention. So it's true for C2 actions. This is work of Bachner, Montgomery. And it's true, and so there's a result that the cohomological dimension of this orbit space is n plus 2. This is CT Yang. So when you take the quotient by the p-adic imagers, the cohomological dimension goes up by 2, which is a rather weird property. And in fact, it took a long time for it to be noticed how this could be used. It was shown for Lipschitz actions. (1997), essentially by comparing the cohomological dimension of this quotient and showing that for Lipschitz actions, the cohomological dimension of the quotient has to be bounded by n. It can't go up like this. This can be weakened a little bit. It's also true for quasi-conformal actions. Martin, 1999. And essentially, all of these results go through this cohomological dimension. But in terms of results which don't put restrictions on the regularity of the action, they're very few. So it's true in dimension 1. This is pretty easy. It's true for dimension 2. This was proved by Montgomery-Zippin around the time of their solution to Hilbert's fifth problem. And it's true for n equals 3. This is a result of myself. Right. So I'll spend a little bit of time talking about how to prove it in the dimension 3 case. So a lot of the tools I'm going to use are going to be from low-dimensional topology, 3-dimension, and 3 manifolds. So we're going to take a break from group actions and just do some 3-manifold topology. So this next section is going to be about incompressible surfaces in 3 manifolds. Okay, so I want to consider the following class of 3 manifolds. So we're going to restrict to 3 manifolds which satisfy the following properties. So I want the manifold to be connected, orientable, irreducible, meaning no embedded 2 spheres. I want the second cohomology group to be Z, and I want it to have exactly 2 ends. So non-compact 3 manifolds. For example, M3 could equal a surface cross R, just a cylinder. And in general, one could call manifolds satisfying these properties quasi-cylinders. So you should think of it as looking like this. I have 2 ends going off to infinity, labeled plus and minus, perhaps. And you can draw a bunch of surfaces which separate the 2 ends, representing the homology class. Okay, so for such a 3-manifold, we can define the following set. So let S of M be the set of surfaces, so embedded surfaces, which are oriented, orientable, such that F is incompressible, or rather, the fundamental group of F injects into the fundamental group of M, and F generates the fundamental group. I consider these up to isotopy. So it's exactly the set of surfaces like this, which are embedded. So as a set, this is perhaps not such an interesting object, but there's a partial order on S. So we'll say that F is less than or equal to G if and only if there exist representatives in G, where F is to the left of G, is what you think. So in symbols, that's F is contained in M minus G, the part containing the negative end. But in pictures, it's just this. They're disjoint, and F is closer to the minus end. So the claim is that this is a lattice, or yeah, let's see. Well, no, let's back up. Okay, so the claim, first of all, is that this is a partial order. So is this a partial order? Well, F is less than or equal to F. This is pretty clear. You can just move F a little bit off of itself, since the normal bundle is trivial. What about transitivity? Well, you have representatives of F and G. You have representatives of G and H. But the two representatives of the representative of G here and the representative of G might not be the same. There's an isotopy connecting one to the other, though, and you simply apply that isotopy to, say, H, and you get that F is less than or equal to H. So this is also easy. In fact, antisymmetry is a bit subtle, though. Suppose F is less than or equal to G, and G is less than or equal to F. Does this imply that F is equal to G? So, as far as I know, to prove this, we really need to use some three-dimensional topology. So the picture is we have F, we have F prime, which is another representative in the same isotopy class. And we have G in between them. Now, since F and F prime are isotopic, this region between them is isomorphic to a product. And incompressible surfaces and products are simply the fiber across a point in the interval. And so this is true. I should say, perhaps for people who don't know, this algebraic condition is equivalent in the orientable setting that we're in to the statement that F inside M is incompressible, which is to say that there don't exist, if this is F, and you have a disk like this, a disk bounding a non-trivial element, an embedded disk bounding a non-trivial element in the fundamental group of F inside of M, is called a compressing disk. And so this F that I've drawn here is not incompressible. It's compressible. So this is a more geometric condition, and it's equivalent to this algebraic condition in the case of everything is orientable and embedded. Okay, so there's a very important property that this lattice, or that this poset satisfies, and this is that it's a lattice. And it was, I was informed of this property by Ian Agel. So this poset is a lattice. in other words, the set X of Fg, simply the set of H, which are bigger than both F and G, has a least element. So in pictures, if you have some surface F, some surface G, then you can find some surface, say H0, which is to the left of everything, which is to the right of both F and G. And this is of a very a rather non-trivial result. I won't say exactly how to prove it right now. I'll just say that it involves the existence of area minimizing representatives for incompressible surfaces and some three-manifold topology. So there's a result of Friedman, Hass, and Scott, which says that when you have incompressible surfaces, the area minimizing representatives minimize the intersections between them. So in particular, if you have two surfaces which can be isotoped to be disjoint, then their area minimizing representatives are in fact disjoint. And that is that's the important non-trivial content which goes into proving this. Okay, so now I can talk about the application to Hilbert Smith Conjecture, namely that there's not a copy of Zp inside the homeomorphism group of any three-manifold. So it goes like this. So first of all, let's recall that we can always assume that the action of Z mod P has small orbits. And what that means is I'm going to be drawing pictures of stuff inside the manifold, and you should think of Zp as the orbits being very small with respect to the pictures. So this is happening inside M. I'm going to pick, let's pick a solid handle body of genus 2. So this is K naught, handle body of genus 2. Okay, and I'm going to let K equal the orbit, union of all translates of K naught. So the orbits are all small, so you should think of K as simply looking on a coarse scale, it looks exactly the same as K naught. It's just sort of grown some wild fuzz in a small neighborhood of K naught. Okay, now I should say that the philosophy of the proof is sort of that we want to do some type of dimension reduction argument. We know the Hilbert Smith conjecture is true for n equals 2, so one way you could try to prove it in three dimensions is you find an interesting Zp invariant open set and look at its boundary. So Zp acts on this boundary, and if this boundary were a two-manifold, then you apply the previous result. So it's not going to be end up being that simple, but this is sort of why you might try to do something like this. Okay, so this is one set. Now I'm going to zoom in on a small piece of the boundary. So here is K, and I'm going to draw a small loop, L naught connecting 2 points on the boundary. So I'm zooming in much smaller than the action, much smaller than the size of the orbits. And so L naught is going to be moved around a lot by the action. So I'm going to say L set L to be the orbit of L naught. It's now a bunch of copies of L naught. So their union I'll call Z. Right, now making this construction complete and correct is a bit subtle, but the important properties. Yeah. L naught. It's a small loop connecting two different points on the boundary of K, and it's made smaller than the size of the orbits. Okay, so Z has basically two important properties. And those are that we get from this construction. So one is the ZP action on the check cohomology is non-trivial. We manufactured this property by attaching the loop. It's much smaller than the diameter of the orbits, and so when you move it around, you get some homology which is also moved around. And the other property is that on the coarse scale, Z looks like a handle body. Of genus 2. So that's all we're going to really need from Z. Right. So we have this interesting closed set of our three-manifold, and I want to sort of look at its boundary. So unfortunately, its boundary is probably rather wild. So it's very far from being a two-manifold, and we can't reduce to the two-dimensional case. We can, however, look at a set I'll call U, which is epsilon neighborhood of Z minus Z. So you should think of this as an approximation to the boundary. It's an open. It's basically an open neighborhood of the boundary of Z. And of course, ZP acts on this approximate boundary. And hence, well, U doesn't exactly satisfy the, do I still have this here? No. Yeah. Yeah. Right. It should be smaller than the loop. So the epsilon is the smallest of everything. It's smaller than the size of the orbits. Preserve U. So I'm gonna take a ZP invariant metric to take the neighborhood. ZP preserves Z, and then I take the Right. Okay. So after I do a small modification to this definition, which I can say more precisely if people have questions, it satisfies those hypotheses that I wrote, for which you can consider this set of incompressible surfaces in U. So this set of incompressible surfaces is well, any such surface can be thought of as sort of an approximation to the boundary of Z. And, okay. The great thing about a lattice is that if you have a group action on a lattice and it has finite orbits, then it has to have a fixed point, because you just take any finite orbit and look at the least upper bound of that finite orbit, and that has to be fixed. So since we have this proposition from Ian Egel that S of U is a lattice, we see that there exists some surface, F inside U, such that ZP fixes the class of F in this set of incompressible surfaces. And this tells you that we get a map from ZP to the mapping class group of the surface. Right, now this action of ZP on F, or action up to homotopy, satisfies two properties which are derived from these properties from Z. So this homomorphism satisfies one. Okay, first maybe I should say that this homomorphism is continuous in the sense that its image is just some quotient z mod p to the k for some k. So some open neighborhood of the identity gets annihilated. So it's continuous for the discrete topology here and the profinite topology here. Right. So the fact that ZP acted non-trivially on the homology of Z tells me that if I choose epsilon small enough, then ZP acts non-trivially on the homology of F. In particular, image is non-trivial, is non-zero. That's all I need. This is not the zero map. Now the second property is that if I look at the homology and the first homology and take the fixed locus of ZP, then it contains a sublattice where the intersection form is given by two copies of the hyperbolic pair. And the reason that's true is because of this second property of Z. See, there are these two loops inside Z, and these two loops outside of Z. And you can sort of project them onto the boundary. And since they're far away from Z itself, they're fixed because the action has small orbits. And the intersection form on F agrees with the linking form on between the interior and the exterior. So since the linking form between these is precisely that, we have this sublattice of the homology, the fixed homology, which has this as the intersection form. Okay, so now I claim this is a contradiction. Simply because there does not exist any non-trivial element of the mapping class group of order P such that this fixed set has this as a subgroup. So in fact, this fixed fixed part always looks like at most one copy of this and a bunch of copies of p times the hyperbolic pair. So I don't actually know a good conceptual reason for why this is true. You simply classify all the elements of the mapping class group of order p, and you look at all of them and say that, and observe that the fixed homology doesn't have such a submodule. So it would be nice to have a more conceptual proof of this last step. Yeah. Why do I act on homology? So, I mean, I act on the mapping class. There's a morphism to the mapping class group. So that gives me an action on homology. Right, so it's because the action on H1 of Z is non-trivial. So if you choose epsilon small enough, then the homology of Z, or the cohomology of Z, injects into the cohomology of F, or perhaps the other way around. It's this, there's a check cohomology satisfies a continuity property, so the direct limit of the check cohomologies of these epsilon neighborhoods is the check cohomology of Z, and that gives you, that it passes to F. So I think I'll stop here and can answer more questions. So I think you do the contradiction is sort of similar. So you pick some ZP orbit, which is sufficiently non-trivial, and you remove it. And then the action of ZP gives you a morphism from ZP to the braid group. And the image is finite, but the braid group is torsion-free. So that gives the proof. So that's the proof that, I don't know if that's Montgomery-Zippin's original proof, but that's the way to prove it. Well, so I mean, a lot of these like tools of incompressible surfaces are very specific to dimension 3. So it's not clear how to do the dimension reduction, I guess. Right. So all the orbits are finite. So right, if I take any particular surface, there's a big power. I mean, there's some big k such that p to the k ZP fixes it, just because it moves it by only epsilon. And so all the orbits are finite, and you take the least upper bound of any orbit, because it's a lattice and it's fixed.